All right, so I wanted to do another example, possibly a trickier example. Let's work it through and find out. So we're being asked to draw the Lewis structure for this OCN minus iron. Um, so we're going to have to count up our valence electrons first, see what we got. So we got 1 oxygen, so that is going to be 1 times 6 valence electrons from that oxygen. We've got 1 carbon, so that's 1 times 4 valence electrons, and we've got 1 nitrogen, so that's 1 times 5 valence electrons for the nitrogen, and it's got a -1 charge, so it gains an electron, so we have to add another valence electron. Okay, so that is going to give us a total of 6 plus 4, 10, 15, 16 total valence electrons to deal with. Okay, so what's going to be the central atom? Well, I guess we're okay writing it O, then C, then N, because oxygen's got a bonding capacity of 2, carbon, bonding capacity of 4, nitrogen, bonding capacity of 3. So we can be pretty certain that carbon is going to want to be in the middle. So O, C, N, like so. All right, so let's join them up with bonds. Okay. Oh, I didn't want that to be that color. Try that again. Yeah. Join them up with bonds, and then give the atoms around the outside some delicious lone pairs. So what have we got here? 2, 4, 6, 8, 10. Sorry, it's messy. 12, then 14, 16 valence electrons. So I've got the total number of valence electrons. That's okay. Does carbon have an octet? No. Okay, so we've got to convert lone pairs to bonding pairs. So this is where it's going to get kind of fun, because it's not equivalent how I do it. Like if I take a lone pair from the oxygen and make a double bond between carbon and oxygen and do the same between nitrogen and carbon, I could do that, or I could do 2 lone pair to bonding pair conversions for the oxygen to the carbon, so have a triple bond and a single bond, or I could do the same with the lone pairs on the nitrogen, making them into bonding pairs, so I'd have a carbon nitrogen triple bond and a carbon oxygen single bond. So this is where the idea of formal charge can actually be very useful. Okay, so let's explore those 3 different options. So, oh, didn't mean to do that. Redo. There we go. Come back. Though, to be honest, I think you've seen that now. I'm going to get myself some more space. So we could have had 3 different options. Sorry, it takes me a while to draw these things. Oh, where's my little thing gone? Okay, so we could have gone symmetrical, like so, or we could have gone asymmetrical option 1, or asymmetrical option 2. Let me fill in the lone pairs so we can see them, and then we'll talk about how we can use formal charge to check and see which of these is the stop doing that. Which of these is the best idea? Okay, so this would give us 2 lone pairs on the oxygen and the nitrogen. This would give me just a lone pair on the oxygen, and it'd give me 3 lone pairs on the nitrogen. That looked rubbish. Make that better. No, it still looks rubbish. Okay. Drawing is not my forte, I'm afraid. But it's as long as we understand what we got here, it's all good. Now that is really ugly. Okay, so how do we calculate formal charge then? So formal charge is the nominal number of valence electrons, so that's always going to be the same because it depends on the position in the periodic table, minus half the number of bonding pair electrons, or if you prefer, just minus the number of bonds. Because remember, the bonding pair electrons are shared between one atom and its neighbor. So if we're calculating the formal charge on one particular atom, only half of the electrons that are the bonding pair electrons belong to that particular atom. The other half nominally belong to the other atom that is bonded to. And then you're going to subtract off that the electrons that are in lone pairs or non-bonding electrons, if you prefer. So we can do that and then get a formal charge. Formal charges should be minimized for the most feasible Lewis structure. Okay, so 0 formal charge is like excellent, or like minimizing the number, whether it's positive or negative. The formal charges on a molecule, which is neutrally charged overall, should all sum to 0 for each atom in the molecule. If you have a polyatomic ion, the formal charges of all the atoms in that ion should sum to the ion charge. And then the last criteria we have using formal charge to decide if a structure is appropriate or not is if there is a negative formal charge, or the most negative formal charge should be on the most electronegative element, because that will be the element in the Lewis structure that is most able to draw electrons towards itself, electron density. Okay, so it wouldn't make sense if you had less electronegative element with a positive formal charge, and then something else in the structure had a negative formal charge. All right, so I'm just going to try and tot these up then. I like to sort of do in a table if we've got to do a few. So the valence electrons of oxygen is 6, carbon is 4, nitrogen is 5. So we'll just go all the way along here. 6, 4, 5, 6, 4, 5. Okay, so then for each of these bonding environments, we are going to decide what minus half, well, I won't minus it for now, that half of the bonding pair of electrons are. So I'm going to move this back. Oops. So for the oxygen, there's 2 4 electrons in bonds. They're being shared with a carbon. So half of those 4 electrons will be 2. Okay. So for the central carbon, there's 2 4 6 8 electrons that are in bonding pairs. So only half of them belong to the carbon, so 8 divided by 2 is 4, okay? The other half belong to the oxygen and nitrogen, respectively. And then for the nitrogen, 2 4 electrons that are bonding electrons, so half of them belong to the nitrogen, so that's 2, okay? Same for this oxygen, 2 4 6 bonding electrons divided by 2 is 3. Carbon, 2 4 6 8 bonding electrons, so divided by 2 is 4. Nitrogen, 2 bonding electrons divided by 2 is 1. Same for this oxygen, only 1 pair of bonding electrons, so 1 belongs to the oxygen, 1 belongs to the carbon. This carbon, 2 4. Oh, hang on, I've lost a single bond in there. Where is that gone? Shocker. So 2 4 6 8 divided by 2 is 4, and nitrogen 2 4 6 divided by 2 is 3. I'm going to add that one back in real quick. Because that's confusing that that's somehow disappeared when I was drawing things. Was it ever there? Did I accidentally delete it? I don't know. All right, so then you're going to subtract off from that the electrons that are in lone pairs, okay? So that's the total number of lone pair electrons. So for this first oxygen, 2 4 lone pair electrons, carbon 0, nitrogen 2 4, oxygen 2 lone pair electrons, carbon 0, nitrogen 2 4 6. Then oxygen on the left, 2 4 6. Carbon 0. Nitrogen 2. And I've just realized I've been really naughty because I didn't actually draw these as ions. Oh, shocker. So let me just fix that real quick, because that is terrible of me to have done such a horrible thing. These are all -1 polyatomic ions. So I fixed it before I stopped recording the video. That's good. I got so excited about needing to use formal charge. I know, it's a sad life that I lead if I got that excited about formal charge, but here we go. This is looking very higgledy-piggledy. Okay, so then what we have to do is take our total valence electrons minus half the bonding pair of electrons, we've already divided by 2, minus the lone pair of electrons to get our formal charge, okay? And this is for each atom. So for the oxygen, this could be 6 minus 2 minus 4, 0. That's a good start. 4 minus 4 minus 0, 0. 5 minus 2 minus 4 is -1. Okay. Remember, they should add to -1 because the charge on the ion is -1. So 0 plus 0 plus -1 is -1. So that's good, isn't it? 6 minus 3 minus 2 is +1. 4 minus 4 minus 0 is 0. 5 minus 1 minus 6 is 0. All right. And then finally, 6 minus 1 minus 6 is -1. 4 minus 4 minus 0 is 0. 5 minus 3 minus 2 is 0. Okay, so first of all, the one in the middle is definitely wrong. Why? Because the charge, 6 minus 3 minus 2, is definitely +1, last time I checked. So the formal charge is just wrong, like totally wrong, okay? Cannot have a +1 total formal charge, okay? So we definitely don't have a carbon-oxygen triple bond. Good to know. So there is a difference between, let's call it structure A and structure C. One has the -1 formal charge on the nitrogen, and one has the -1 formal charge on the oxygen. So bearing in mind what we said about electronegativity and having the negative formal charge on the most electronegative element, remember electronegativity increases towards the top right-hand corner of the periodic table. Well, ignoring the noble gases because they suck. No, because they don't want to attract electrons towards themselves because they have a full valence shell already. So fluorine is the most electronegative element. If it helps you to remember that, you can either think of it as being increasingly like non-metal in terms of character, because remember, metallic character increases towards the left of the periodic table and down a group. Or you can think of it in terms of effective nuclear charge, because we know that as we go across the period, effective nuclear charge is increasing because Z is staying the same, and the amount of the shielding is staying the same, and Z is increasing. Therefore, the valence electrons are feeling a higher amount of nuclear charge as they go across the period, which means atomic radius decreases, etc., etc. So think about it in terms of effective nuclear charge. If more of that positive nuclear charge is being expressed, then that would translate into being able to attract electrons towards itself, right? Because, it's positive and electrons are negative. So out of nitrogen and oxygen is the most electronegative, right? It's most towards the top right-hand corner of the periodic table. So if we had to choose, we're going to choose this one based on formal charge considerations.